Hello everyone, let's talk about another medium problem on Leetcode today. Delete nodes and return forest, Leetcode 1110. In this problem, we are given the root of a binary tree where each node in the tree has a distinct value. Then we have to delete the nodes in it such that after deleting all the nodes with value in toDelete list, we are left with a forest, a disjoint union of trees. We have to return the roots of the trees in the remaining forest. We may return the result in any order. Let's look at some examples now. So in example one, we can see that we are given the tree like this, and toDelete list has elements 3 and 5 in it. So we delete 3 from the list and 5 from the list. So in this case, we will return the list of tree nodes, right? So in the output, we will return this root, and this root, right? So that is why the output is 1 to 4 for this tree, 6 for this tree, and 7 for this tree. And this is what we are returning here. Now let's jump into how we can actually solve this problem. So generally speaking, delete is slightly harder in the tree because we have to keep the tree connected. So for example, if I delete 3, then somehow we have to either replace it with 6 or 7, depending on the criteria the problem has stated. But here we don't have to do that. It can stay disconnected. So that's why we get the forest. So it is easier to solve the tree problem with recursion. So we do the DFS and then we try to find out the node which we have to delete and then just delete it. So for example, if we found out 3 here based on a delete list, so we will just return null, right? And the node is basically deleted. Similarly, when we found out 5, again the node is deleted. So we will just return null here. Deleting 5 was okay because it does not have any children. But for 3, we need to keep the reference of its children, that is 6 and 7 somewhere, because they are part of the forest. Because if we delete it during the recursion, we will actually lose the access to these nodes. So how about we do this deletion in a bottom-up manner? Hear me out. So this is slightly confusing when we think about this algorithm this way. Is like, because we cannot easily delete here, even though deletion is trivial, we still have to do it in a bottom-up way because we need to have the reference to its children to return it as an answer. So when we are deleting, we have to just take care of two things. When we are going top down for doing the DFS, we actually mark the node for deletion. So we just don't delete it. We will just mark it. And once we mark it, next time when we are coming bottom up, we will just delete it. So why we need to mark it? The reason is that if we mark suppose 3 for deletion, then we know that the children of 3, that is 6 and 7, can be root of next trees in the forest. For example, if we delete 3, then we know that 6 and 7 will now become the root of the new trees. So we have to collect the root of these new trees and return it as an answer. So this was the idea. Now let's see how we can actually devise the algorithm to solve this problem. So let's look at the first example again. So first thing we will do is, because toDelete is a list, we will convert it to the set. And the reason for this is because for each node, we will check whether this node has to be deleted or not. And that will take O of n time if it's a list. So better thing is to use a set, because then the lookup will just take O of 1 time. Then we start the DFS. First thing we check is if the current node is null. We will just return, because if it is null, that means we have reached the bottom of the DFS and we should return because we don't have to delete anything here. Then the next thing we check is if this node has to be deleted. And suppose the answer is yes, then we will just mark it for deletion and let the next DFS know that this node, the parent of these children, have to be deleted. So that's why now they can be the new roots, provided they are not part of the toDelete list. So they can be actually added to the forest. Let's look at the example. First thing we do is, like, we create a set of 3 and 5, right? Because those are the nodes that have to be deleted. Then we start the DFS with node 1. Does it have to be deleted? The answer is no, because it is not part of toDelete set. Then we go down. 2. Does 2 have to be deleted? The answer is no. So then, is 4 has to be deleted? The answer is no again. So then we see, is 5 have to be deleted? The answer is yes, right? So we mark it as yes, it has to be deleted, and then we go to its children, but it does not have any children. So we will come back to this node and just delete it. So we will just return null. And so far we have not added anything to our forest yet because it does not have any children. So it does not create any new root or anything, right? So then we continue. We come back to 2 and then come back to 1. Then we go to the right side, again do the DFS. So does 3 have to be deleted? And the answer is yes. So mark this for deletion. Don't delete it yet. And then we go to its children. Is 6 has to be deleted? The answer is no. But does it have a parent that has to be deleted? And the answer is yes. So we will add it to the forest. So now our forest will have 6 in it. Then we go back to 3 and then go back to 7 now. So we see, does 7 have to be deleted? The answer is no. But does 7 has a parent which who has to be deleted? And the answer is yes. So that means 7 is a root of another tree, and that's why we add it to the forest. So now we come back to 3. Now we delete the 3 and return it back to 1. So we can see that now this whole tree is gone. So this is disconnected. Now we come to the root node, that is 1. And we already saw it was not part of to delete set. So that means it has to be part of the answer, because if you remember, we have to return all the trees in the forest, and this was the original tree given to us, and given we didn't delete it, so this should also be part of the answer. So don't forget this edge case. So we will also add 1 to the list. So all these values are added as a tree node, not like normal integer value. So that's it. I think writing the code is comparatively easy, but this was really good recursion, because we have to collect the forest going top down, and we have to delete the nodes bottom up. So this was like a tricky recursion. This question is asked by farm companies, mainly Amazon and Google, I think. I hope this was clear. Now let's jump into the code part. So first thing we do is we convert the array of to delete to set of to delete. Now we will just initiate the forest and pass it to the DFS. So we will just say, okay, delete nodes, and we can pass the root here, to delete set there, forest there, and whether the current node is root or not. So we will send true here, and the DFS will return the node. If it is deleted, then we will get null. But if it is not deleted, then we will get the updated root. And then we will just return forest. And now we write the recursion code. So we can see in this function, we pass the current node, the release set, and the forest. So we will add the collected roots to this forest. And is root is true whenever there is a potential that the current node can be a root and has a potential to be added to the forest. For example, when it is the real root, in example 1, when 1 was a real root, or the parent of the node is deleted. For example, when 3 was deleted, 6 and 7 will have is root equal to true. And we will return the tree node. So again, if it's deleted, we will return null. Otherwise, we will return the tree node value. So let's see how this will work. So if node is equal to null, we will return null because we reached the bottom of the tree. Now we will check if this node has to be deleted, and how we will check is to delete set dot contains node dot well. So if it is deleted, then we will just mark it for deletion, right? And if it is deleted, that means we will just return null. Otherwise, we will just return the node. But before deletion, we should actually update our forest. So now we will recurse to left and right side of the tree for updating the forest. We will just go to node dot left. We will again pass a to delete set. We will pass the forest, and instead of passing true, we will pass is deleted, right? Because if the current node is deleted, that means the children of it can be the root, right? So I'm always using can be, because if it's part of to delete set, then maybe they cannot be root, and that their children can be the root. And similarly, we will do the same thing for right side. We have to update our forest as well. So what we will do is, if we have is root equal to true, that means current node is root and it is not part of the deleted set. That means we will add it to the forest. And note that we have already taken care of the edge case here, because for root, we are already passing is root equal to true. And if it's not part of the deleted set, it will be automatically added to the forest itself. So yeah, that's how the whole logic will work. Now let's run this code. Awesome. Let's submit this code. Cool. In terms of time complexity, it is O of n, where n is the number of nodes in it. Because we are going through each node only once, so that's why it takes O of n time. And in terms of space complexity, it will be O of h, where h is the height of the tree. But in the worst case, it can be O of n as well, because we are doing the recursion and we are using a recursion stack. Also, we are using this set here. So in the worst case, they can say that, okay, delete the whole tree. So again, it will be O of n. So both time and space complexity is O of n. I hope this solution was useful to you. If it was, please like and subscribe. Have a nice time. Thank you.